So today I'll present Titans, Learning to Memorize at Test Time, which is a paper released by Google and essentially an extension to the attention models. And so today I'll try to go through really four main sections, which is why do we need Titans at all, how they actually work, the different kinds of architecture, and how do they actually perform in the field. So we'll start with just some background information and understand why we need Titans. So I'll start with just a very brief review of RNNs. Also, whenever I explain something, please stop me if you don't understand something or ask me questions. I love to ask questions, so it helps. So I'll just quickly go through RNNs, which is recursive neural network. And the basic idea here is you have some input tokens, which are X, like your X's. You have some output token you're trying to predict, which is the in series. So, for example, if you have a sentence like a cat ate, I don't know, a mouse, like a cat caught a mouse, every single token is going to be at a certain T, at a certain location, and you're going to try to predict the next token. And we have a hidden state in between with recursive neural networks. That's kind of how they work and how they allow you to keep stacking on more and more tokens and keep doing inference. They're really nice because you have a fixed size of computation every single step, which allows you to have, even if you have a really, really long sequence, just adding on one more token, as long as you've done everything before, is just that one same, like the one additional step. And there's also like the same size in terms of memory. So the hidden state here, which is called S, which you can see has its own way of being written, which is basically a nonlinear model, is going to allow you to carry information from one computation to the next. So an example is like if you're predicting something like, I like coffee. Okay, I cannot handwrite today. I don't know what's happening.
Your handwriting's good.
Like your very first hidden state will be some trained number. And then you'll have your first token, which will be basically your I. And you bring in that information, and here we'll, let's say, do like, the prediction is going to be like, which actually is correct. And then we bring in a state that was computed from the word I using this formula on the right. And so that will give us our new S1, which we'll use for the next prediction when we predict what comes after like. If that makes sense. And so this is actually really nice because in a way you can compress every single information in the past into a single hidden state, an S state, but it has some pretty bad problems as well, mainly that this is lossy. I mean, you're compressing a lot of information into a single hidden state. Obviously, you can't have an infinite number of information into the 256 size or 512 size vector. And so obviously you can't hold that much information. It's all going to be compressed somewhat intelligently by the model. At least that's the hope.
So when you repeat this process, Z1 would become the input?
Z1 here would become the next input. Well, it would be an additional input for tokens, I believe. This is just like to bring some quick review. So it's not quite the most important, but the idea here is just when you bring in this new sequence of tokens, yes. Like, as that makes sense, yeah.
Like the general idea is like you start off like some initialized hidden state. Just if you're doing like English to Spanish translation, right? Like X1 through like XT are going to be your English words.
Yeah, so that would also be like a way you can.
Okay. And then like another question: are the thetas are just weights, right?
Thetas are weights here. Yes, they're all weights, and your sigma here in this case is just going to be, as I said, like a nonlinear model. I'll go more into depth for exactly what everything means when we get into the actual architecture. This is just meant to be like some background information to try to help you build the intuition. But there's some problems. We're not going to solve all of them today, but I just want to bring them up with RNNs. Mainly, you're going to have vanishing and exploding gradients when you backpropagate. That's simply just the way that RNNs are being trained. And if you know more about backpropagation, you might see why when you actually go more in depth. There's a lot of limited context memory because every time you're only looking at one token and whatever came before it as a hidden state, which if you know a bit more about attention, you might realize that this is one of the main things that it's able to solve, where it's able to look at a bunch of tokens at once and then make an answer from there, except like a bunch of those tokens are going to be initially set to 0, basically, or the null token. And there's also a sequential dependency. So that means that you need to compute every single hidden state before the one you're currently at. So it's kind of, you know, a win-loss in terms of, like, on one side you win the fact that this is a fixed size hidden state and a fixed size computation every time. And on the other side, you just need to compute a lot if you have really long sequences. And then a few years later, Berkeley and some other people realized RNNs are fun, but we can improve them by making them being trained during test time. So what does that mean? And like this is kind of the more important information for the paper, is instead of having a hidden state, this is actually going to be a model, this W function, and it's going to be trained during inference. So as you're getting more and more data, you're going to update this, hidden state. This is slightly different than what we had before, so I'm just going to be between the two here, where before it was just like a fixed model that was just already trained. Here we have a memory which is actually going to train while being while running on new information. So it's a bit different than your regular RNNs. But the main idea here is now, because you have a machine learning model, this allows you to improve with respect to the testing data. And that might be really useful, for example, if you trained on, let's say, a lot of book data, like just random books, like novels written by really smart people, but all of a sudden you're moving on to something really informal, and your model will actually get better at working with that informal text, because it wasn't explicitly trained on it, it was trained on different text, but it's getting better and better with that particular text, particularly with respect to memory. And so this is just going to be what is called test time training and TTL layers. Does anyone have questions kind of about how that?
Yes. Alex, what is the formula for the loss that we're computing?
I don't remember exactly for this paper, but I believe here it's just going to be, the loss function is just going to be some mean squared errors.
With respect to what?
Like to the prediction of W, like whatever the current state, like the predicted state would be versus what it is with the new token that you're given.
But it's self-supervised learning, right?
Yes.
So how is that working? Where we don't have a target label.
Well, here the target label would be like whatever is the next token is. So if like you're using W0,
Yeah.
you're trying to predict like what X1 will be essentially. And likewise. So you're using whatever previous information you have to kind of understand what will be the next X state. Like again, this is not the main purpose of the paper, but I believe here it's just going to be about like improving your memory over time to predict what is going to happen in the future.
So each iteration of RNN is performing a single weight update, and that weight update is computed with respect to the ability of WT-1 to predict XT.
Yes.
Okay.
I saw some other.
And that is not using the input.
So that's using the input X of T.
Right. Well, I mean, for example, for computing W0 or sorry, W1 is W0 minus.
Right. It will be W0
and
minus.
the gradient of L W0 with X1. So we don't have input tokens when we are computing this at all.
Yeah. So here you would start with W0, which would be a really bad prediction. But the hope here is that because you're able to learn more and more as you get more data, you're able to compress more intelligently the data, particularly if it's different than what you were trained on. So it still has like the very similar core idea of having that hidden state. It's just now that the hidden state actually gets better over time, hopefully.
So WT is updated.
WT gets updated, yes.
And so does ST, right? Like in the previous slide?
ST, yes, but it doesn't, it's just like a direct, like it's a computation that just already, like all of the weights here are already trained with just testing data, not like with training data, not testing data. So here you update it with respect to X, but you don't do any real changes based on what X is.
Okay.
So if you had like a really weird X, like this is just going to do the same, well, roughly the same computation as you would have. Like, it's not going to be smart about how it infers X. It's just going to be trained to do X or
I understand now what the motivation is. One last question. Now with this update rule that we have, we are in the normal feed-forward process, we are just substituting xt with wt, and so we have sort of a theta that goes from that transforms w1 to z1 and x1 to z1 similar to the previous slide.
Yes, it's still going to be the exact same computation for basically everything else.
Okay.
It's just going to be the idea of how do you update your SFT or your WFT here.
Okay. And are we setting a prior? I guess one more question, but I'm sorry. Are we setting a prior for W0? So now during the real training time when we're actually training, do we train W0?
I believe so. Yes.
Okay.
It's going to be like a lot of things here, like that n is going to be a weight that's going to be trained, like the learning rate is going to be trained, like a lot of things here are going to be trained at training time. Like you're going to train how to train essentially, which if you think about it is a little bit like what you do when you do hyperparameter tuning, like kind of train to train. Here it's basically doing that on much earlier and a much larger scale.
Awesome.
Question?
Yeah, I'm a little bit confused. Can you elaborate more on the loss function? Because like where and again, it's fine if you're like not 100%.
I don't fully remember exactly on that paper. I can check afterwards if you want, but like I'll go more into that for like.
At the high level, like you're just trying to like find a smarter way of updating your weight versus blindly multiplying by the same fixed parameters.
Exactly.
Okay.
That's the idea. And I mean, even though in regular RNNs, it's a little bit smarter than just the same things because you will have like multiple layers to update that, like an MLP. But here you're updating that over time. Okay. So that's really the core idea is TTT, test time training, allows you to train on the test data.
So like at every single time step you're doing a gradient update?
Basically.
How slow is it? If you've looked into it.
Actually, it's, well, for this model, I'm not quite sure. For the Titans, it's actually pretty fast. Okay. Like, it's not, like, it's a very small model that you're going to be updating. So, assuming you have any sort of GPU, like, it's going to be non-noticeable.
I have the,
assuming H100.
Wait. Like, so I opened the paper link, right, that's there over there. And if you want to open it, maybe it might be easier. Page 4 has a table. It's the difference. There is no cost between naive RNN and naive TDT usage, the test time training. It's still O1 compute. So there is no, I don't think there is any significant overhead. Right?
I think for the Google papers, they did find some slight overhead, at least during training to train. But during testing, yeah. So here it's going to be, if you have self-attention, you're going to have T. Here I think they're talking about like the cost with respect to computing the new S, like the new token is going to be with respect to 1, just because like you're only taking in one new token in like previous states.
And solution 4 on page 7 also has the loss function.
On page 7?
Yeah.
Yeah, right here. So so that's what I thought. It does look like it's some sort of it's some sort of squared error, but that doesn't look like it's pure mean squared. But anyways, like this is not the main paper we're talking about. I was just bringing it up to kind of give like an understanding of what we're actually looking into. Now, any more questions, by the way? Okay, so I'll move on to what we're actually here, which is Titans. How do we improve upon that? And the very quick answer, which some of you might kind of see if you have a experience with attention models, is let's combine attention and long-term memory. But we'll see how long-term memory actually works. So they're going to improve upon what we just saw. Right before that, here's some paper notation. So if we ever need to refer back to them, like it's going to be very similar, but they kind of change some of the math conventions. But just to be clear, it's going to be X your input, Y your output, memory unit, which is essentially going to be one of the big hidden states, is going to be called M. The write operation is going to be F. So like, given the previous memory state, how do we compute the next, with the previous memory state and a new input, what is going to be the new memory state M of T? And the read operation is how do we predict the next output? And here your loss is again going to be L. So it's slightly different than the previous one where we had W of T. Now it's going to be M of t. That's basically the main change, but I just want to make sure everybody's clear with those for the rest of the paper. So here we're kind of going to go a little bit more into depth into how we update things with respect to LLMs. The most important idea here is going to be you want to make changes based on how big of a surprise you have. So how big of a difference between what you were predicting and what you actually got is. And here they call that delta. Basically your delta L, which is going to be how big a loss is how unexpected is that next token. So if you're predicting I like, and here, like if you said cats, that would actually not be that unexpected. Like a lot of people like cats. But if you said I like IU, very surprising. No one would ever say that. And so here your surprise would actually be really big. And so you would want to change your memory state by quite a bit. And I actually just showed that live by the fact that some of you laughed, and you'll probably remember this quite a bit because this was surprising to you as well. And so hopefully that makes it easier to see intuitively how improving memory based on surprising facts will actually improve the model, because now we're able to learn what are surprising facts, what are interesting, and make sure we keep track of them. So that's basically going to be your core idea, and it's just going to be the gradient with respect to the input. So how different is, basically what is going to be your loss, and like how far are you from what you wanted to predict, and just let's go that way. It's basic gradient descent. But Google is actually a bit smarter than that. They thought, actually the data right after that prediction is still really important. So we're going to consider your past surprise as well. So whatever your surprise was before, we're going to consider it as well, in addition to the surprise right now. Essentially, if you just heard like some really important information, in terms of the intuition, if you heard some really important information, you don't want to just lose whatever was there. You want to keep going a little bit, which basically is going to be gradient descent with momentum, where you do gradient descent on what the information you just received was, and the momentum is going to be whatever previous surprise you had. If you notice, like N of t, theta of t, those are going to be parameters that you're going to be training based on the data that you're actively getting. So S of t is going to be your momentum, in this case, like the past surprise. And then, yeah, so you're going to have like your functions, which are going to have all of those parameters that you're going to tune over test time. And again, same thing for theta of t. Does that make sense with everybody? Because that's kind of the core idea of how it works. And it's a little bit different. Like there's a slight difference to how they did it previously with RNNs with TTT. But does that kind of make sense on how now we improve memory, I guess on a psychological view? Yeah.
Can you talk a bit more about what is like the difference between SFT and MFT?
SFT is essentially what they're going to be calling the, I guess, yeah.
Like how's SFT minus 1 computed? Like how's
SFT minus 1 is just whatever previous, like.
Sorry, how's S0 computed? The base case.
S0 is going to be something that you're going to be training, like during your main training time, you're just going to train whatever S0 is. Like that's that simple. Like it could be all zeros for all we really care. Like as a human, you might put it as all zeros, like Gaussian noise. The model is going to train whatever that is as a parameter.
So what does it mean that NFT is data dependent?
Data dependence means that, I should explain more on that. So when you have like your I like IU example, you're going to essentially change, you're going to change entity based on that information. So based on what X of t is. Well, in this case, mainly what the previous surprise is, which is going to be a function of X of t. So whatever like your new data is, like your X of t is, that's going to help contribute to whatever essentially your S of t minus 1 is going to impact your S of t. And that makes, like, it's going to depend on whatever new information is brought up.
If the new information is like more surprising, will that make it larger?
So I believe here the idea is just like if you shift topics enough, your past surprise won't really matter as much. So it's more of an idea of, it's just a function of x of t, which is essentially going to be an MLP. Like a lot of things here, like function just means multi-layer perceptron. So it's just going to be, however you impact your past surprise depends on whatever the token is that you're currently on. Does that make sense?
I have a question. M0 is also learned similar to F0?
Yes. That's to the best of my recalling abilities. Yes. Okay. And lastly, this is one of their other ideas, which is going to be for the loss function. So this is how it's slightly different. That's why I didn't want to go too much into that previously. Is you can see those are people who like attention because they're going to do associative memory, which is trying to replicate a human phenomena where you try to associate certain topics together. And here they're going to do that with using t-pair values. So it's very similar in a way to transformers with attention is all you need, where we're going to have your WK and WV, which are weights that are going to be learned. Those are just going to be learned like during the main training time, if that makes sense. Like your main learning is going to learn what WV and WK are. So that's also why I wanted to make sure before, like M is memory, W is going to be for those main weights you're going to learn, and that's going to give you KT and X of T, and that just allows you to compute loss more intelligently, which in a way is just saying like, this is just a better loss function because now you consider how tokens, like how, more interestingly, how a token works, if that makes sense.
Surprise M for MT minus 1, this is a function?
MT minus 1 is your previous memory.
Right.
So whatever memory state you had before.
Is this, state, this is a state, so it's a vector?
Yes, so memory state is like whatever you had before. I believe I get it here. Like M of T, M is like an R of D vector.
R of D, okay, gotcha.
Again, that's why I put that slide up there so I could make sure I could reference to it. So did that kind of make sense, like the associative memory idea? At least at some basic level, like we're just trying to improve how we compute how bad we are.
So I have a question about the key value pair, right?
Mm-hmm.
The idea behind, or like in self-retention, we have a query and key, and we are performing the correlation between the query and key. That's how we determine how correlated two entries are and how much the attention should be paid to them.
This is not a full attention.
Right, yeah.
This is just like a general, like it's kind of that similar idea here, but what realistically you will have is just your X of T WK multiplied by M of T. So
But
you'll have.
What does this mean? Like, I mean, I guess I'm struggling to see semantically how that is equivalent to, or like why is it called a key value pair?
Oh, that's because they like to call it that. I don't really know more than that. They call it, they basically call those key values because they look very similar to key values in attention. Like, I don't have a better answer. That's how they called it in the paper without much more discussion.
Like, I mean, intuitively, if WK and WV are 0, loss will always be 0.
Sorry?
If WK and WV...
Those are trained during the main training time.
Yeah.
So
if you just during the process of learning, right? If they learn as just the zero matrices, isn't loss going to be 0 because both of MT minus 1 KT
right.
and VT will both be 0.
So I'll try to answer that by kind of splitting it in between two halves. So on one hand, you'll have like your training, like main training.
Yep. And
on the other one, you'll have your testing. So the loss with respect to testing, if like WK is equal to WV, which is equal to 0, during training, I'll actually start with testing. During testing, you're going to have like L of MT minus 1, X of T. That's actually going to be 0. You're completely correct. But during the main training, having that 0 testing actually is pretty bad because it means that you're effectively telling your model, oh, you're perfect all the time. But your model isn't going to be perfect all the time.
Right, yeah, so why does this work? How can we use this loss? Are we not using this loss function here in training?
Not during your main training. Well, it is going to be used during your main training, but like on the different, we're training the model that you're training, if that makes sense. Like,
sorry, I'm a little bit confused.
sorry, yeah.
During training, what is the loss function that we're using?
During main training, sorry, give me a second, I'm trying to recall. I think they don't explicitly mention the main training way. It's just going to be backprop with whatever you use for your LLM training. Yeah, basically.
But then in this case, so the key value weights, right? The key value weights don't. How do they affect the feed-forward process? Because this seems to be only for computing surprise, right?
Right. So this is for surprise, which is one of the things you're training to train for.
So in the feed-forward process, the output of the token is going to be the predicted next token, right?
Right.
Or like the logic for the next token, and then we backpropagate with respect to that. But if in the feed-forward process, WK and WV are not involved, we won't have any gradients.
They are involved. Sorry, yeah, I should be. Okay, yeah, I see what you mean. They do remember. I think what they did here is it just. Okay, I'm gonna move a little ahead, but I think it's just going to be essentially like because it's going to be one of the parts of the architecture. Is going to be training that, like computing what the next token is given previous information. They're just going to be considering those W, V's, and WKs. Can I get back to you on that at the end?
No problem.
I need to think through it, but I don't want to spend all the time on this question. But I do see like this is a question that I need to answer. And then lastly is just going to be the forgetting mechanism. Essentially, if you have a lot of tokens, like millions, you're going to want to forget a little bit of past information. And so they just added that vector here, A of t, which is basically going, well, it's all a vector, it's just a value 0 to 1. Essentially, you're just going to want, well, actually no, I believe it is a function with respect to x of t, so I should be more precise. But it's effectively going to give an output between 0 and 1, just telling you how much to forget of previous memory. So if you have a really long token of sequence, like a really long sequence of tokens, you want to forget maybe, I don't know, like 2% of what you had before. And just giving more information. This isn't amazing, but it is going to give you adaptive forgetting, which is going to be a smarter way to manage your memory than just having a constant in there. Does that make sense? Any questions about how this works, like if I wasn't clear or anything? Or okay. Let me continue, and now we're going to get into like a little bit more interesting, which is the actual architectures. So what are going to be MAC, MAG, MAL, and LMM. And just to get into that, I want to point a little bit more attention into how can we combine different types of memory. So you're going to have short-term memory, which is going to be attention. I just want to give a quick recap on various types of memory. So short-term memory, and like how Dave drew it in the paper. Short-term memory is attention, like an attention is all you need. You're effectively working with a really small section of tokens. And I'm calling it small because 200,000 tokens in this case is considered small. Because they're talking about the scale of millions of tokens. So when we talk about long-term memory, which is that MLP that we're training over time that I was talking about for the last 15 minutes, that's going to be your long-term memory. Shorter memory is attention, so it's going to be precise token to token, very like fixed context window. Like attention is pretty bad at growing or shrinking. You kind of just do with whatever amount of data you have. So if you have a lot of data that can only fit 15,000 tokens, you can't really train a larger model easily. You'll just train on that 15,000 tokens. And it's very useful for critical immediate context. What that means is if you're going to do math or like writing English or any smart things, I guess I should say, anything that requires you to just have short-term attention. So if it's just like predicting what is going to be the next word, what's the next step in an equation, all those things are going to just be very short term memory actions, which are great for attention because you're just trying to be smart there. Long-term memory, is a lot more dynamic, so it allows you to have a much greater size. It has that idea of encoding. So the idea here behind encoding historical context and patterns. Essentially, whatever data you just learned, you're able to use it for long term. And if there was something really interesting that you learned before, you're going to be able to use it in the future. But everything non-interesting, you kind of forget it, but smartly. You don't just cut it off. You're going to cut it off smartly. And then there's that idea of persistent memory, which is essentially a way of just learning basic rules of the world, like how English to some extent works or how math rule works. They call that persistent memory, and we're going to very briefly go into it. Okay. Here, I don't know why Google sites are weird sometimes. They're going to cut off a tiny bit. But anyway, so persistent memory is a set of learnable weights. There's just going to be a bunch of learnable weights that you're going to have in there. And the idea is kind of weird. Like, it took me quite a bit of time to understand why they were doing it, and they have justifications. Actually, I should maybe just show one of the diagrams that they're going to have. Like, learnable weights are basically going to be a bunch of tokens you're going to add before your sequence. So that's why I'm going to say they're a little bit weird. I'll go more into this memory as context right after, but I'll keep the diagram up just so you can see, like, this is kind of weird. And the idea here is going to be those sets of parameters right here are essentially, they give them three perspectives, but they're essentially going to be whatever memory you have to just learn how to do tasks. That's their memory perspective. Essentially, like, doing math is going to be the same regardless of what input you have, what tokens the person gives you, and so that's where you're going to learn it. If you look at it from an FFN perspective, they're basically quoting some other authors who said, hey, in transformers, right after attention, you have a bunch of layers for your MLP. And if you replace those with a softmax instead of ReLU, with WV and WK, those are essentially going to be they're basically going to be, sorry, I lost my, those are basically going to be, relatively speaking, input independent when you use softmax. They're basically not going to care as much about X. It's kind of weird. I'm not 100% sure on why they're explaining it this way, but that's one of the perspectives they give. Essentially, is in transformers you have the same thing, just if you do some minor changes, and that's what happens right after your attention. And that's one of the ways that they do WV, WK here, but it's not the same thing at all. Like, it's not your memory module. This is just long-term memory. Yeah.
So I have a question. So I kind of see the vision here. We have like persistent memory below, which is just the learned parameters you're training. Then the upper part, the neural memory, is that like the hidden state of the RNN? And then attention is, the attention module is just standard self-attention. So we have long-term memory, short-term memory, and then just knowledge. Is that the idea?
That's basically the main idea. That's what I was trying to get at with this kind of recap.
Okay.
Is that's going to be your main idea. I'm going to go more into this graph in a second. I'm just keeping it up there so again you can see kind of what your fixed memory, like what your fixed tokens are going to be, which again are just going to be that persistent memory. And from the technical perspective, which actually is a much better justification, they're essentially found, like, I mean, it should be reasonably obvious when you work with attention that a lot of, there's a really big bias towards caring about the earlier tokens with attention, because when you do your mask, you basically take half of the attention off because you can't predict the future, so you only look at early information. And that actually creates a massive bias towards earlier tokens. So by having persistent memory right at the beginning, you're essentially forcing your attention to not have that bias and learn to avoid that bias. That's one of the justifications they give, which I think is one of the.
Is this something that they see, like the attention?
Yeah, they said that it's an implicit bias. That's basically quoting that. This is not an exact quote, but that's kind of a paraphrase of what they're claiming happens. Again, because of that causal mask that you have when you hide the second half of attention. Like, you know when you have attention, like...
Yeah, the causal mask, right?
Yeah, you hide all this. They're basically saying, like, there's an implicit bias towards caring about those first few parameters. And, like, they kind of just stated, I think I might have linked to a paper, so I can go back through that. But
in their trained models or the final models that they get after it, do they show that it's more uniform? How do they verify like the actual case?
trust me, bro.
Okay.
That's basically a lot of their paper. But yeah, so that's going to be the idea at least. I mean, it kind of makes intuitive sense because if you add different fixed information in the beginning, it doesn't, like, if your model only cares about that, it's not going to be good. So hopefully it will very quickly learn to not care as much. Does that kind of make sense to everybody? Okay. So now we're going to get into MAC. Essentially, everything we've covered up to now, we're going to put it all together. So you're going to put all of that persistent memory before your, here's a sequence and a sequence of inputs, so a sequence of tokens. You're going to use that to make a prediction about what is the next token going to be. You're going to use whatever tokens you predicted, put it before, and now you have a much greater sequence of tokens. Feed that to attention, use that to update like your current M of T, which is that RNN that we've been training during test time. So that's why the update happens here all the way at the neural network stage, as opposed to before. And then we're going to use that and just like basically use a gate to decide which we're going to use more together. If that makes sense. So essentially, we're just throwing it all together. Using our long-term memory as part of attention is also something pretty important. Essentially, we're allowing our attention model to know what happened in the past. Yes?
So basically, your complete input, so like the model will, I don't want to say model.
To attention, if you want to say?
Yeah, sure, yeah.
No,
so your input to attention is going to consist of like your knowledge, right?
Mm-hmm.
And then in addition, you're going to pass your sequence through your RNN, which will give you like the important like surprise information that you want from it.
The update is going to happen later, like that's the second
thing. Sorry, I guess I'm confused about the
So this part right here is just going to be like compute what is expected, like what is the current state and what is expected to be the next token.
Oh, I see.
Like what is the next, like what is the expected, next value, or what they do with their f of t essentially. Okay. Which, if you can think of it, if you make a prediction, that's also a way of like knowing what everything came before. Okay. So that's what all they're going to do here, and like you can think of it as just throw everything together and hope that it works well. Their second main architecture is going to be MAG, which is going to be slightly different now. Instead of feeding that long-term information into attention, because that's actually kind of slightly computationally intensive, we're just going to do them in parallel. One side we're going to do, again, that long-term memory. On the other, we're going to do attention, still with that knowledge persistent, like that persistent knowledge, and we're going to use some gating at the end. In a way, this is separating your long-term and short-term memory and only unifying them right at the end. Yes?
Do they talk about which gating they use? Do they just like concatenate it, take a max?
Sorry?
Do they like, just take a max pooling between the two layers? Do they like average pool?
I think there's a bunch of ones that they talk about in the paper.
Wait, am I confusing gating?
But like, I'm not sure that's how gating works.
Yeah, that's pooling, right?
Yeah, just take like the maximum.
I think here it's just like a learnable weight of like you just pick whichever one.
Oh, so you pick either the output of one or the output of other?
Or like I think they combine them with just an MLP like for gating.
Oh, okay. Sorry.
I'm pretty sure that's how it works from the paper. It's just a gating essentially.
Okay.
Yeah. And if you want to kind of see, like, this is how they really compare MAG versus MAC, at least in practice. So in MAC, which is memory as context, every time you're going to have a little bit of short-term memory on which you're going to take a full idea of what your long-term memory is, and then your persistent memory. So if we go back up, like, you're going to have all three of them work at once, but here they use the sliding window. Because like on every token you need a new set, if that makes sense. Like, because here you're using all of them at once, so it's basically just going to be a sliding window on each new set of tokens. Versus MAG, where you're still always going to have that persistent memory, but instead your long-term memory is going to be used more and more, at least as you're getting closer to what you're predicting now. So really old long-term memory doesn't really matter. But now you're going to use really important new long-term memory, and that's where you use basically a sliding window of attention, which is based on how far you are, but you still don't fully disregard because you have that gating mechanism. Does that make sense for everybody? Like, this is maybe not the most important part of the paper, so, but it is something that they consider kind of implementation-wise. And lastly, so this is going to be a little bit of the last two that they cover, which is MAL and LMM, which is memory as a layer and just not even having attention, which is just, if you just have long-term memory, how does that perform? Long-term memory that's trained over time, which is very, very similar to what we saw right in the beginning with RNNs, where you just have an RNN at test time. It's very, very similar. So memory as layer, again, still going to have a window attention like MAC, so where you consider like with a gradient essentially, how like over time the most important information is what's right now, and you're going to feed the output of neural memory directly into attention and then never look at it again. This is pretty bad in the sense of you're no longer separating your long-term memory and your short-term memory. But it's also pretty good because computationally you have to do fewer steps either in parallel, and you can just stack kind of like you're having a transformer, stack one step on top of another. So just a different architecture that they looked at. The idea here is just going to be computationally, is it going to be cheaper, and can we just stack things on more easily rather than having them all done in parallel? Yeah.
So on the previous slide, just looking, does it make sense to have like squares above the diagonal? I guess like what is?
Sorry?
I'm seeing like memory above the diagonal.
If you can predict the future, yes, but like in the sense of the model, everything above the diagonal you don't really have access to yet. The reason why they have some right here is it's just that sliding window with those predictions for the future. And persistent memory. What?
Is that intentional?
The fact that it's like sliding over the window?
Yeah, over like above the diagonal, that implies, what does that imply?
I don't think there's a specific implication other than just what you would predict happens with your, this is what you would predict to happen with your long-term memory module.
My interpretation was that the persistent memory is kind of just concatenated over, and then the tokens are not really, like it's like two columns that are added in between the standard attention mask. So if you kind of ignore those tokens, you will just get standard short-term memory, right? Like the green bar is the long-term memory. If you just ignore them, you just get the standard short-term memory. So my assumption was that you're still causal in nature. It's just that there are extra columns just for attention to attend to some aspects of long-term memory. Does that make sense?
Yeah, I mean, again, like this is very similar to what you have when you do like attention, where you have a set of tokens existing and you can't really predict future outputs. But here they're just showing them as like sliding windows, a little bit over-exaggerated to kind of.
Right. So with long-term and persistent memory, the size of those attention matrices should also increase, right? Like they've not shown it, but it increases. Is that the case or no?
Long-term memory, well, in theory, because you're just outputting like a predicted state, in essence, it shouldn't really grow because it's a consistent size. Like you always add on more information to the same model. Same thing for persistent. Persistent is always going to be the same. So that's why they're always going to be the same size. But I think here just they keep looking at previous states of long-term memory. And LMM is you just disregard the attention altogether. So that's kind of what they did to just make sure that the idea of LLM, long-term memory, works on its own, which to some extent you're basically saying, let's disregard attention, let's make sure that Titans work on their own, like the idea of long-term memory works, without having to necessarily rely on just making a bigger attention model, like a bigger GPT or whatever. And let's quickly compare some of the performances. So how do we actually perform with Titans in real world? So if we look at language modeling and common sense reasoning, which is effectively most of what you do in the real world. So either you're just trying to predict words like information, or reasoning is like answering questions like math or like solving riddles. Here though, I'll zoom in just, I don't know how well you guys can see on the other one. Simple, what they call a simple model is essentially one where you don't need to mix in multiple things at once. So like you don't need to like MAC, MAL, and MAG, all three of those are not simple, they're hybrid because you have that long-term memory as well in there. They consider LMM to be simple because you don't have to mix attention and LMM, it's just LMM, long-term memory. And essentially you're going to see like they're really good. They do really well. You're going to see mainly that it's going to be MAC and MAG that are going to do the best. It kind of makes sense intuitively because here, in both of these cases, you're separating your long-term and short-term memory, and then later on combining them. Whereas MAL is a little bit left behind because here you don't have that abstract level of distinction. You don't really separate them, you just have them stacked on top of each other. Yes.
So what's common sense reasoning?
So I think the way that they define it here is there's going to be like tasks like riddle or math, or like if I put a coffee pot on the table, I leave the room, where will be the coffee pot? Something like that, I think, is what they mean by common sense. But those are just going to be regularly used, like all regularly used metrics to determine how well a model does, at least model architectures. And here you'll see, like on average, basically, no matter the size and the number of tokens you have, they're still all going to be basically the best. With MAC, roughly speaking, at the top, but like not really far behind by MAG. They consider mostly that actually, which is pretty interesting, MAC does much better when dealing with much longer dependencies in data. Like if your long-term data was really important, like really old data, MAC will actually do better. So the very first one, memory as context. This is just a finding, so they don't have like a particularly better result as to why. The idea here is it's just more complex, and because you use it in attention, hopefully you would be using that long-term information better.
What do they mean by a hybrid model?
So that's what I was mentioning, when you use both attention and long-term memory.
Okay.
When you don't use both of them, like if you just use attention or just long-term memory, it's going to be a simple model. But here you can see like you're going to have your learning and your in-context learning. And then needle in a haystack, which is actually one of the main tasks that you'd want if you want to have really long data. Yeah, it does well. So just very quickly going through it. Essentially here, needle in the haystack, just
So yeah, I'll just go by that. Do you know what the context length is for the needle and haystack task?
I think you're just going to, well, I know here they have a sequence length.
That's what I meant, yeah. Okay.
Like, but I don't remember exactly for every single metric on top of my head.
No, you're good.
But I think they're just going to be like different types of complexity for each metric, and then just ask until you can. So essentially the idea of needle in the haystack, just to give some context, I have a really long token sequence. Let's say I give you a book and ask you, what did Harry Potter say to Hermione after XYZ? That's needle in the haystack. Or I hide a secret sentence like magic cat at the very beginning of a dictionary, and I ask you, what is a word that comes before magic cat? And your model might actually struggle with it, particularly in attention, where it might struggle with long context. Here with LMMs, you're just able to do really, really well. Essentially, even compared to something like GPT-4, which are really big models, your MAC and your MAG, yeah, I mean, they don't explicitly say how big their MACs and MAGs are in number of tokens, not number of parameters, sorry. Like, they don't tell us, but it's reasonable to say, given like at least previous data, that they went up to 30 billion, went up to 700 parameters with 30 billion tokens. So hopefully it's within up to 8 billion parameters. Like, I don't exactly know how many they had for those tests. I can double check. But essentially, even against much, much, much larger models, your MAC model is able to do really well over really long periods of time. And again, even if you fine-tune your model to do even better, it's able to go up to 10 to the 7th with reasonable accuracy. Really, 10 to the 6th is going to be better, but you can see in terms of just raw accuracy for a needle in a haystack, that's going to be a massive difference, which is one of the main reasons you'd want Titan at the end of the day, is you just want to have longer sequences and not rely on RAG, which if some of you know, hopefully you can realize why that would be such an improvement. And an ablation study, so they just compared like different types of MAL and exactly why certain combinations work. I didn't go over exactly every detail about linear memory just because they did various tests of convolution, momentum, weight decay, and persistent memory. I think the only one I didn't really go into was a convolution step. But essentially, you're going to see how Mac-Mag are very, very similar. But Mac is going to be stronger, at least over long periods of time. And both of them are going to be faster than Mac and Mag. I didn't include the graph for that, but that's just like informing you on their findings. Also, they call that common sense, so shame on the Google for not proofreading. Any questions? Okay. And yeah, thank you for your attention.
I have one question about, so in the paper they mentioned a 1D convolution.
Yeah, so that's a step that I was just here, like I gotta skip that one just for the sake of time because it was harder for an intuitive answer.
Okay.
But I can go into it with you if you want. So yeah. Yeah.
Your personal opinion, do you believe in this? Do you believe this is the way?
The way, it's always the way, but I actually really like it, particularly for multimodality. Like, for example, videos. Like, a lot of models struggle with videos just because you have so much data. So I hope that we can implement things like this for video transformers. So that's kind of, in thinking, I guess, like for robotics, like just test time during training during test time makes a lot of sense, particularly if your training data is different than your testing data. So, in my opinion, it makes a lot of sense, and I think, like, I can't guarantee it, but there's a very good chance that Google implemented this a while back with a lot of their models, and that's why they're basically the only ones who will offer, like, models that allow you to have 2 million tokens, as opposed to, like, Anthropic with only 200,000 tokens. Like, they already beat the competition by quite a good, I don't know what the right word is, like by quite a big like margin already, yeah. And like here, their empirical testing again, like to compare it to just GPT-4, they're just beating it like out of the water with just few shots. And if you fine tune it, you'll get even better. So if you compare like again Titans to what you would use in the field like GPT or like Llama, there's no difference really. Like, just use Titans. So yeah, like I do think that it is a really good solution.
Do you know if they released the model weights?
Good question. I think they released the code. I'm not sure about the weight.
Half of Indiana is computer trained.
But like if, yeah, I'll check on the paper. I'm not quite sure if they do have them. I can check. Give me a second.
I'm surprised they would, because like if this is like a backbone for everything that they're cooking on Gemini, then like not like hiding the parameters makes sense. But yeah, dude, it just takes like 8 trillion parameters. Don't worry about this.
I mean, they said it's under a billion.
Under a billion?
Yeah, this is under a billion.
Yeah, okay, that's what I thought. It was a 960 million.
They have multiple variants, all are under a billion. There's 360 or something like that. So
I was thinking of the one by Berkeley, the first RNN with test time and training. That has code. I don't think they have any code published.
340, 400, and 760 million parameters for the evals, the ones we just saw.
Oh yeah, so it was just going to be those ones, basically, is what you're telling me, right? Like it's 240, 400, 760? Yeah, okay. That's what I thought. I wasn't 100% sure. I don't remember off the top of my head, but yeah. So essentially, they're just going to use this really large model, and that's how they beat GPT-4. So yes, probably.
What about other tasks, like for non-needle in a haystack with standard perplexity? How does it perform on that?
I think that's closer to language modeling, common sense, which again, they're going to beat a lot of like similarly sized models. I don't think they would beat anything remotely as difficult as GPT-4. At least if it's not long enough, like here, you have 30 billion tokens of length, like.
Right.
Well, actually.
I mean, this is more so just size. Like,
yeah, I mean, here, again, like the entire point is to have that long-term memory, not that short-term attention. So, if you're asking about, like, if it was a task which relied on long-term memory, yes. If it was a task that doesn't rely on long-term memory,
it doesn't do so well.
Well, it won't really change anything. You'll just learn to rely.
Well, I mean, the thing here is they aren't even using attention as the main thing. Like the big one is LMM, and they don't use attention in LMM. So this is just recurrent networks.
Right, for LLM, yes. But that's, again, mostly focused on long-term choices. But, like, on short-term things, like, there's a lot of papers about RNNs that are pretty old by now, like, that were released right after attention, or right before. Basically, attention will blow it out of the water. Like, attention is really good for that short-term memory, and they're very clear about the fact that that's not their fight here. Their fight is really, like, adding those two sections, not this.
Right.
It's really long-term memory and persistent memory, that's what they're bringing to the market. So you can think of this paper, like if you had to tell someone why Titans is a paper, tell them it's attention part 2, like do this, how do we complement attention?
Right.
That's kind of the idea, so yeah. Any other questions? Right.
Thank you.
Thank you.
Awesome. Thank you.
Also,